They're not the same thing, but they're both situations that we do deal with in the lab. Now, we talked about K a long time ago, and K is basically the same as Q. It's just not necessarily going to be at equilibrium. And that's the case here. We don't know, so we would have to go through our calculations using the K that we had put together in our two examples previous to this. Okay? So, now, what the heck does this mean right here? Well, great question. R, if you recall, it should look somewhat familiar to you, is the ideal gas law constant. Now, in the past, we've had 0.0821 liter atmospheres over mole Kelvin. The problem here is G is calculated in terms of kilojoules or joules, depending on how you look at it. The charts that we look at in this thing is measuring kilojoules, and we'll talk about how we're going to do that in just a little bit. But the value of R here has to be expressed in terms of joules instead of liter atmospheres over mole Kelvin. All right, and the value for that turns out to be 8.31 joules per mole Kelvin. So that's the constant we're going to use instead of 0.0821. Temperature, of course, is T, and again, that must be expressed as Kelvin instead of Celsius. And then Ln means natural log. You do have a natural log key in the calculator that you would have to use for this. Why natural log, not regular log? Well, we could if we put another constant in there, which I don't think we were real crazy about. Since you do have an Ln key in the calculator, we're just going to live with it. And K, again, is products over reactants in a mixture of gases and aqueous solutions that we just talked about. You put all this together, and you can calculate this. If you're trying to find delta G, you would subtract this quantity from this, and that would give you your calculated delta G values in terms of standard conditions, and then you can compare your values to the book if that's what you're so inclined to do. All right. So, the issue with the R, and let me talk about that real quick. Since I said R is equal to 8.31 joules per mole Kelvin, but these two G's here are calculated in terms of kilojoules, and on the chart they're listed as kilojoules, then what you would need to do is change this over to kilojoules. So we multiply this by 1 kilojoule over 1,000 joules, and we get a value of 8.31 times 10 to the negative third. The joules cancel out here. So that'll give us kilojoules per mole Kelvin. And that really is the value that we need to be using in these calculations, so you don't have to make any sudden mistakes because you have different labels on different parts of this equation. So use this value instead of the 8.31 that I gave you because that's in the wrong label. Okay, so let's take a look at an example here. It says find the standard free energy change at 25 degrees Celsius. So T equals 25 degrees Celsius. And then if you add 273 to that, that gives us 298 K. And again, put my 2 cents worth this, that should be the standard, but it's not. For the reaction H2 gas plus Br2 liquid, in the script that I gave you, I have a single arrow, and technically it's so large in one direction that it is, but in actuality there's a little bit of what we call backwash, which it does go back about a little bit. So they represent with one arrow in the script, which is technically correct, but since we want to talk about this in terms of equilibrium, we're going to use the double arrow. But if I want to kind of more accurately describe what's going on here, it's more like this. Because it's a lot to the right, a little bit to the left. Okay. And we want to find the value of K for this. Now, so here's the thing about that. At equilibrium, That means that you have the reaction going to the right has a particular delta G value. And then if you go to the left, this has a particular, I'll put delta G sub R, and this has a particular delta G value. And I don't know offhand what it is, but it's not important. And the reason why it's not important is I'm sorry, we're going to use the non-standard form. So let's fix that. G sub R, G sub L. So we have these two values taking place at the same time. The problem is they're going in opposite directions. So it turns out that delta GR is equal to negative delta GL. Now why is that important? Because if you have equal but opposite quantities of heat taking place between two reactions occurring simultaneously, the overall delta G value, which is delta GR plus delta GL, is 0. Okay? So, if that is the case then in our equation here, where we have delta G is equal to delta G standard plus RT natural log of K, K now becomes Q because it is now at equilibrium. So now we're dealing, I'm sorry, it was Q, now it's going to be K. We had Q, now it's going to be K because it is at equilibrium. This now becomes 0. So now we see a relationship here where we can find this value on our chart using the products minus reactants for the various components in any reaction. And then we can plug in this stuff right here, and then we can solve for K, because we don't know what K is, but we do know R, we do know T, because it's 25 degrees Celsius. So that means then that if I subtract this and get delta G by itself, delta G standard, this is equal to negative RT natural log of K. And this is the equation we're going to use for this problem. Okay, so that means then I can find delta G by going to the chart and taking, now remember, let's go back to, I really do not like the attitude of this board today. So let's rewrite the equation here. We've got H2 gas plus Br2 liquid yields 2 HBr gas. Okay, so I need to take the 2 times the delta G of HBr, which is 199 kilojoules per mole, minus the sum of H2 gas and Br2 liquid, and according to the charts there, I have for those values 131 plus 245 kilojoules per mole. So when the smoke clears, my value for this is 20.0 kilojoules per mole. So I'm going to put in 20.0 kilojoules per mole right there, equals negative, and now we're going to use that kilojoule version of R, which is negative 8, which is at 8.31 kilojoules per mole Kelvin, times the temperature, which we said is 298 K, times the natural log of K. So now I'm going to divide this by this whole thing right here with the negative sign. So I'm going to divide that over here, and I get negative 8.08 equals the natural log of k. Now, I don't know how much you remember from your logarithm chapter in Algebra 2 or Pre-Calc, but if you want, this is not ln times k, this is a function, the natural log of k. So we need to get rid of the natural log, and so we have to do the inverse of the natural log, which is, now the natural log, again, to refresh your memory, is the logarithm base e, known as Euler's number or the natural number. So, and logarithm means exponent. So to get rid of that, we take e caret to both sides, the natural number or Euler's number taken to those particular exponents. Well, the exponent of this, by definition, is k. And then we punch that into our calculator, and we get 3.10 times 10 to the negative 4. Now, the meaning of this value is simply that this is well less than 1, which means it's going to go is not going to go hardly at all to the right. It's going to go mainly to the left. So what I had written up there was actually wrong. It should have been a little bit to the right and a lot to the left. So that was an assumption I made that was incorrect. But regardless, this is what we should end up with. So you have the practice problems on there. It's 52 to 58 on page 834. Have fun.